So again, we're going to start with some review. This is day 38, but we're wrapping up chapter 6 about centers. And I want to talk about classifying triangles. You might remember that we were able to classify triangles two ways. One way is by the angles associated with it, and one way is by the sides associated with it. When we classify by angle, what we're doing is we're looking for the largest angle and saying if that angle is acute, then the triangle overall is acute. If that largest angle is right, then the triangle overall is right. And if that largest angle is obtuse, then the overall triangle classification is obtuse. And then we also had the ability to classify by side lengths. Sometimes you've got a triangle where every single side length is a different length, and that's called a scalene. Other times you've got a scenario where two sides are the same, and the third one is different, and that's called isosceles. And lastly, you could have a scenario where all three sides are the same, called equilateral. And you may remember that we did things like give you a couple of angles and make you figure out based on what you're given, classify this triangle. And of course, we could theoretically do it by angles or by sides. And then we could do the same thing over here. If we were given a triangle and we knew that this was 3 and this was 4 and this was 6, we could classify it either by angles or by sides. But prior to this unit, you were limited. If you have this information, would you be able to classify it by angles, by sides, or by both? What do you think?
I would do that one by angles.
Sounds good, because you'd know that, okay, we're missing one. We always have to know the biggest angle. And we don't yet know if that's the biggest angle already shown to us. Can we just claim acute because 50 is the biggest angle shown? No, we're going to have to say 40 plus 50 plus x equals what total? What do all three angles add up to?
180.
Yep. And so when I put this together, I'm going to find that x is equal to 90. Okay. So now that I know that, that's my biggest angle. So that's the one I care about. I rank that. Is that acute or obtuse or right? That's a right angle. Therefore, I can classify this whole triangle as a right triangle. Easy peasy, right? What about on this one? What's the low-hanging fruit here? To go by angles or by sides? Be hard to classify. Good, good. It would be hard to classify it by angles because we don't have any angles. But we do see three sides, and they're all different numbers. Therefore, we can classify it by sides pretty easily. We see that all three sides are different, so we'd classify this as scalene. But up to this point, up to chapter 6 that we're in right now, we had to leave this open because we didn't know about the angles, and we had to leave this open because we didn't know about the sides, right? Well, that's no longer true. We learned last class about something called the triangle inequality theorem. And what that said is that when you've got a triangle, the biggest angle faces the what?
Biggest side.
Biggest side. So we expect this to be the biggest side. And since 50 is less than 90, but more than 40, we expect this over here to be the mediumest side. And this side opposite 40 would be the smallest side. Well, if these angles are all different numbers, what's going to be true about the lengths of all these sides?
They're going to be different.
They have to be, don't they? Because if we saw that, for example, these were both 40 degrees and this was 100 degrees, where a pair of interior angles were the same, then we'd be able to apply the converse of the isosceles triangle theorem to say that that's an isosceles triangle. But we don't have that. Here we've got three different angles, therefore we can say that the three different sides are going to also be true. So we can, in fact, when we're given three angles, classify it by both angles, as we saw first easily, and by sides with our new triangle inequality theorem. Any questions on that? If I want to find out if this triangle can be classified as acute, right, or obtuse, think about right triangles. Now, we've been talking about this thing called the Pythagorean Theorem, and I've told you that I'm not a fan that we're presenting it now because it hasn't been proven to you yet. And the other reason I struggle with having it introduced so early is it's a theorem, which means I should be able to express it as a conditional statement, if then. And most geometry students know that a squared plus b squared equals c squared is the Pythagorean theorem, but it's really only the conclusion to the Pythagorean theorem. What's the hypothesis to it? Under what conditions does the Pythagorean theorem work?
If it is a right triangle.
Very good. It's got to be a right triangle. And the other condition is that C can't be any old side. C has to be the hypotenuse. And then A and B are the two smaller legs. But in that condition, a right triangle with hypotenuse C and legs A and B, then the sum of the squares of the legs is equal to the square of the hypotenuse. That's the theorem. And it turns out that this goes both ways. In other words, if you can put together three sticks, A, B, and C, such that the sums of their squares equals the square of the third, then that's going to be a right triangle. So let's figure out if this is a right triangle or not. Well, we need to know which one's C. Which one would C be? Okay? Crack myself up sometimes. Which length must be C? Good. 10. Why, Lucy? How'd you know that?
Because it's across from the legs.
Okay, but you're still assuming that these are legs. But we know that since this is standing alone over here after the equal sign, doesn't it have to be the biggest number? Because if I put the biggest number here in B, by the time I square it and I square some smaller numbers, of course it would add up to more than C. There's no way C as a smaller value could equal the sum of a positive number that's bigger and anything else. So C has to be the biggest. So I would look at this and say 10 has to be C. And then which one's A and B is irrelevant. You can put them in either order you want. What we're trying to figure out is that true? I put a little question mark on top of my equal signs. I don't think that's real math, but it makes sense to me. Is it true? Well, 36 plus 64, is that equal to 10 squared, which is 100? 100 equals 100. Ah, it worked. What does that tell me about this triangle?
It's a right angle triangle.
It is a right triangle, that's right. Right? If it works with Pythagorean theorem, then we know it's a right triangle. Now let's try another one. Let's try 5, 6, and 7. These are the three sides. And if I want to plug them into Pythagorean theorem, I'm going to choose the biggest one to be C. And I want to find out if 5 squared plus 6 squared equals 7 squared. Okay, so this is 25 plus 36 is supposed to be equal to 49. 61, nope, that's not equal to 49. It's actually greater than 49. So what we now know from this one is what? What can we say? Is it a right triangle?
Acute.
Might be acute. Definitely not right. Agreed? We know it's not right. Because if it were, these two would have equaled each other. So to decide between acute and obtuse, I'm going to ask you to visualize a right triangle where these are the two legs, 5, 6. And do you agree that out there somewhere in the ethos, there is a right triangle with lengths of 5 and 6? I can put those together and find a hypotenuse that works. It does exist out there, it's just not this one. And if it did exist out there, we'd know that this hypotenuse is supposed to make this part the same as this part when I square it, which means the hypotenuse would be the square root of 61. So that when I square it, I'd get 61 equals 61. But that's not the scenario we're looking at here, is it? Ours is 49 when I square it, which means that ours is the square root of 49. 7. Is that bigger or less than 61, square root of 61? What do you think? Square root of 49 less than square root of 61? Or is the square root of 49 greater than the square root of 61?
It would be less than the square root of 61.
Of course it is. So our leg, our hypotenuse, is only going that far. It's not quite as long as it's supposed to be, which means when I take my 6 and this hypotenuse and my 5 is going to have to tilt in a little bit to meet this, won't it? So instead of it having this nice right angle here that it used to have, I've just cut into that right angle a little bit, haven't I? So 2 people actually said this correctly to me privately. What do we think? What happened to the right angle? Is this pink triangle now acute or obtuse? It's acute because it's pinched in. Now, let's actually write out the rules here because it's easier if we just have the rules. So that's what this space is for. We know that if a squared plus b squared equals c squared, then what kind of triangle is it? Then it's a right triangle. If a squared plus b squared is less than c squared, is greater than c squared, so that our hypotenuse is too small. Those two sides have to pinch in to meet that smaller hypotenuse, and so that makes it an acute triangle. If, on the other hand, a squared plus b squared is less than c squared, so the hypotenuse is too big, then that hypotenuse is pushing those legs wider, breaking that right angle in here, and instead making it bigger, obtuse. So let's try this one, 3, 4, and 6. What's the hypotenuse? It's got to be the 6. So 3 squared plus 4 squared might be equal to 6 squared. 9 plus 16 might be equal to 36. 27 is 25. 25 is not equal to 36. But then look at the hypotenuse. Is it too big or too small? Is this part too big or too small?
Too big.
It's too big. So it's pushing the triangle open. Instead of it being a right angle, this would be pushed open to be obtuse. And because all 3 sides are different, we'd say scalene. So this is obtuse. Okay.